So, we are in a position now that using the separation of variable method, we have separated r theta phi equation. So, we have three equation. So, that is basically we are telling phi equation and r equation and theta equation. So, we will solve one after another and find out the form of this function, r function, theta function and phi function. Okay. So, this so let us find out the solution for r equation phi equation. So, phi solution, that equation was d 2 phi by d phi square plus m l square phi equal to 0. So, this is a second order differential equation. Okay. This is the standard equation and its solution is generally one can just seeing the form of this one. So, one can write phi equal to a e to the power plus minus I m l phi. Okay. So, basically people can take the trial solution e to the power I m phi. So, then put here and then one can get the form of this function capital phi. Okay. So, this the basically for this equation, second order differential equation, this kind of equation, standard equation and form of its solution is this. Okay. Here a is an arbitrary constant, right. So, now this function, general function is this one. Now, always we normalize the function, and what is the normalization? As I discussed that to confine the function within some space, within some region or within some limit. Okay. So, generally we consider this the probability, total probability, whole probability is 1. Okay. So, here, so what is the limit of this phi? What is the limit of this phi? So, phi is limit is 0 to 2 pi, right. So, within 0 to 2 pi, so this it will cover the whole region, okay, whole angle. So, normalization phi star, this I already mentioned you, phi star phi d phi within this limit integration. So, that you will be equal to 1. Okay. So, that is the, so this is the phi star phi d phi, that is the probability to find the particle within phi 2 plus d phi in this angle range, d phi angle range. Now, if I integrate over the whole region, so it should be 1. So, if you just put this phi equal to this and then integrate, and you will find out that a, that arbitrary constant is 1 by 2 pi. So, now we have normalized wave function, that is phi equal to 1 by square root of 2 pi e to the power plus minus I m l phi. Fine. So, now also we have to get the realistic, wave function which will describe our system, right. So, we have to adopt the wave function with our system, real system. So, in reality, that this function phi, it has to be single valued function. So, boundary condition basically is coming because of the this demand requirement. So, phi has to be single valued function, means at one place, at one angle, it should have only one value. Okay. So, now you see this phi limit is 0 to 2 pi. So, basically 0 and 2 phi angle, these are same point, same point. Okay. So, phi value has to be same at this phi equal to 0 and phi equal to 2 pi. Okay. So, that is the boundary condition. So, phi value has to whatever this at phi equal to 0, that should be equal to the phi at phi equal to 2 pi. Okay. So, now this you have this phi, it has to obey this condition, boundary condition, and if you put here, so you will get basically A equal to A. So, A is this, that we know, but for convenience just we are using A. So, A equal to A e to the power plus minus I 2 pi ml. Okay. 2 pi ml. Now, to be equal to this, so this has to be 1 e to the power this here. So, this part has to be basically this part has to be this 1. So, this is nothing but cos 2 pi ml plus minus I sin 2 pi ml. Okay. So, from here, so this has to be 1. So, that means this has to be 0, this has to be 0 and this has to be 1. So, cos 2 pi ml has to be 1 plus 1. So, only it is possible when ml equal to 0 plus minus 1 plus minus 2 means any positive and negative integer value. Okay. So, here now we can recognize why we consider ml. We could consider any other constant, but ultimately nature of it could come like this. So, since we are in both theory or this earlier discussion, we know this ml is constant, okay, and it has some integer value. Now, here you see this because of the restriction, because of the boundary condition. So, this quantized value has come automatically. In our earlier discussion, so everything was ad hoc, but here in natural way this number, this constant has come out with some specific values, and we are familiar what is this type of constant. It is nothing but the magnetic quantum number. Okay. So, this ml is called magnetic quantum number and its value is 0 plus minus 1 plus minus 2 and whatever we have seen earlier. So, that has come from Schrodinger equation automatically. So, for phi equation, what is the solution? Phi equal to 1 by square root of 2 pi e to the power I ml phi. So, plus minus I have not taken because ml itself we are taking plus minus integer value. Okay. So, this is the solution of phi equation, and from here we saw the nature of the wave function. So, later on we will discuss some physics from this solution. So, let us now first get solution of all three equations. So, this is the solution of phi equation. Next we will see the solution of theta equation, say. Next we will see solution of theta equation. Okay. So, theta solution of theta equation. So, what is that equation? So, this equation 1 by sin theta d by d theta sin theta d theta capital theta by d theta plus L plus 1 minus ml square by sin square theta. So, this theta function is multiplied with this equal to 0. See, that is the theta equation. Now, we have to find out the solution. We have to find out the solution for this equation. So, note that it is phi equation. The solution is quite quite simple, but for theta equation and r equation the solution is not very simple. One has to know really mathematical physics. You have to be familiar with some standard polynomial. So, from mathematical physics or from mathematics one can learn that one. So, one is Legendre polynomial and another is or Legendre function also one can tell, and this other one is Laguerre polynomial or Laguerre function. And then you know, here I do not know this other kind of functions, the Bessel function. So, the standard some polynomials are there, functions are there. Okay. So, it has, so that function satisfies some differential equation, okay, means that polynomials are the basically solution of that differential equation. Okay. So, here the, this our theta equation, whatever this present form. So, it is not representing any equation of known polynomials. So, but here we will see that this theta equation, this basically it follows the Legendre polynomial, it follows the equation of Legendre function. Okay. So, so we will now basically one should try to reformat, one should try to reformat this function, this equation to the form of Legendre equation. Okay. So, that is what we will try, and that is the how to do that one. So, one has to follow these steps. So, here, so we will put z equal to cos theta, okay, and use sin square theta plus cos square theta equal to 1. Okay. So, now, so here basically in terms of d by d theta it is there. So, we would like to write it in terms of d by dz in that d by dz in that form. So, here we have d theta by d theta small theta. So, this now here this this z is a function of theta. So, I can write dz by d theta, and again now this capital theta, when theta is replaced by z. So, now capital this theta it will be function of z. So, one can write d capital theta by dz. So, basically here you can see it is basically equal to d capital theta by d theta. So, d capital theta by d theta can be written in these two terms. Okay. So, dz by d theta is nothing but minus sin theta. Okay. So, minus sin theta, and this is there. So, this d by d theta, this operator, okay, will be equal to minus sin theta d by dz. So, we replace d by d theta by minus sin theta d by dz. So, that is what one has to do first. So, and we will use sin square theta plus cos square theta equal to 1. So, sin square, so 1 minus sin square theta equal to z square, or sin square theta equal to 1 minus z square. So, these things we have used, and one can write this one, okay, this equal to 0. So, now it is the standard format of this called associated Legendre equation. Okay. This equation is standard equation, associated Legendre equation. Okay. Why associated? So, this I think is basically Legendre polynomial, Legendre function, is there. So, now associated because here two terms will be there. So, this function only this L term, so that is called Legendre polynomial, but when this m is associated with this function, so it is called associated Legendre function. So, this is written PL ML is a function of Z. Okay. So, this equation basically nothing but this phi it's since it is Legendre equation, associated Legendre equation. So, this phi is basically this not phi, this theta, capital theta, this is the function of theta, function of Z. So, this equation will be satisfied when this theta will have this is equal to this Legendre polynomials. So, Legendre polynomials is written like this. Okay, PL. So, it has expression that we will see, but it is the notation for writing this Legendre polynomial. So, solution is basically theta equal to this Legendre function, associated Legendre function, and some constant. All the time we write some constant, and later on we have to normalize and find out the value of this constant. So, B P L M L a function of Z. Okay. And Z, now you can replace Z equal to cos theta. So, this is the, so B is arbitrary constant. Now, one has to normalize. Now, normalization here theta, this it can change the angle from it is the angle with the Z axis, right, angle with the Z axis. So, it can change the angle from 0 to pi, okay, with Z axis 0 to pi it can. So, angle is theta with Z axis. So, it can 0 angle and then at a pi angle. Okay. So, this limit is 0 to pi theta star theta. Now, sin theta d theta equal to 1. So, here we have not taken d theta, we have not taken d theta, right. Sin theta d theta we have taken. Why? Why we have taken this? Because you see this we take always elementary volume in Cartesian coordinate, elementary volume V dV equal to dx dy dz, right. In spherical coordinate, that elementary volume dV is basically, if you write, so r will be extended r to r plus dr, means it is extended dr, then angle change by d theta. So, its theta is there, angle theta. So, this is r. So, now you change by angle d theta. So, this change will be this arm of this say cube, it will be r d theta, okay, and this other angle is with the x axis. So, we take the projection and this on xy plane. So, this projection, that is that distance r sin theta. So, r sin theta form the angle phi with the x axis. Now, then you are taking d phi angle, if you just change d phi angle. So, this change arm, this small change, that is elementary change, it will take r sin theta d phi. Okay. Now, you have dr one side, another side r d theta, and then third side is r sin theta d phi. Okay. So, that will give you this elementary volume in spherical coordinate. So, dr r d theta r sin theta d phi. So, here I have explained. So, this is dr change r change to dr, the small elementary this length dr, and then d theta change. So, it is r. So, it is r theta, and then projection I have taken here. So, of r. So, this r sin theta angle make with this x axis this d phi. Okay. So, so this will be this elementary change due to this d phi will be r sin theta d phi. Okay. So, as if this one. So, this elementary volume is this. Now, this we have written this r here, from here you can see one part is r square dr, r dependent, another part sin theta d theta, theta dependent, and another is d phi. Okay. So, when we will normalize, okay, r part, so here there we will take r square dr for theta sin theta d theta and for phi d phi. So, earlier we have seen only I took phi star phi d phi, okay, but here theta star theta sin theta d theta we are taking, sin theta d theta we are taking. So, that is the reason in normalization why I have taken sin theta d theta. So, this has to be 1 within this angle, particle has to be there. Okay. So, this this from this normalization one can find out is, as you know that this phi is not in simple form, it has Legendre polynomial. So, Legendre polynomial, associated Legendre polynomial from tables for different value of L and ML, one can get the expression, okay, this that function, okay, form of the function, and one has to use that. So, calculation are lengthy. So, we are not going to do that. We are not going to do that because we are interested to discuss the physics, but we need mathematics of course, but since it is tedious calculation, we will try to avoid that calculation, but we will write the result as it is available, but only discussing the step, how, what are the steps and how to find out. Okay. So, here if I normalized, so then this b value, this normalized this b value which comes really this was square root of, here third bracket I have given, in second bracket 2l plus 1 by 2 into L minus ML, this ML, yes, and this one is, yes, and L plus ML. So, here, yes. So, this is the B part basically, this is the B part, and PL ML whatever here it is there cos theta. So, that is there. So, this B part is this, and then this function form are there. So, explicitly we will use when we will discuss physics. Yes. So, now this PL, so this is associated Legendre polynomial. So, there is a Legendre polynomial. So, and it is related with this associated one. So, this how they are related? So, this PL ML Z, this equal to basically 1 minus Z square ML by 2 d ML by d Z ML, okay, PLZ. So, this PLZ, PL as a function of Z, this is called the Legendre polynomial. Okay. When it is another term ML is comes, so then it becomes, it is called the associated Legendre polynomial. Now, Legendre polynomial and associated Legendre polynomial, so they are related like this. Okay. Okay. So, so details form will in general we will not discuss, but we will discuss taking some particular value of ML L, we will discuss some physics out of that one. Okay. And this P and this form of this linear function is here is 1 by 2 to the power L factorial L dl by dzl z square minus 1. Okay. So, this is the Legendre polynomial. Okay. So, this is the solution of the basically solution of the theta equation. It looks very complicated, but do not bother this calculation, only one has to know how it is calculated, but if one sit and systematically calculate, one will get the result. So, for next I will show you the solution of R equation. Solution of R equation, this is also very lengthy calculation, but in this case this equation is 1 by r square d by r square dr by dr plus 2 mu h cross square E plus z d square by r minus L plus 1 h cross square divided by 2 mu r square, or function of this function r capital R equal to 0. Okay. So, this equation we have seen earlier. So, now we have to solve this one. Again here this is not the standard equation, this is not a standard equation, but one can take it, one can adopt it to a standard equation. So, that standard equation, differential equation of it is one can convert to the associated Laguerre polynomial. Okay. Associated Laguerre polynomial. So, this associated Laguerre polynomial, this is generally we write L q p function of say rho, okay, and that differential form. So, it satisfies the differential equation like this, okay, rho d2 by d rho square plus p plus 1 minus q d by d rho plus q minus p this L q p function of rho. Okay. So, this is the form of the Laguerre associated Laguerre polynomial. Okay. So, now this equation is, one can see it is quite close to that. So, one has to convert this equation or reformat this equation, adopt this equation to this Laguerre polynomial, Laguerre differential equation, and then we can write the solution of is this Laguerre polynomial, associated Laguerre polynomial. So, for that there are few steps, and the steps again it is again very lengthy calculation. So, I will not do all. So, here my aim is to show you how naturally this quantum number has come up, whatever was considered in our earlier discussion, that n principal quantum number, L azimuthal quantum number, angular quantum number, right, orbital quantum number, and this ML magnetic quantum number. Okay. So, this was considered on ad hoc basis. Now, the same things how it come out from this quantum, from this Schrodinger equation in natural way. So, that I would like to just emphasize that part, just avoiding details calculation. So, in already we have seen what is ML, how it has come. So, that has come basically from the phi equation, okay, from phi equation, and the restriction of this restriction was it has to confine within 0 to 2 pi angle, and from single valued function because of that. So, value has to be same at phi equal to 0 and phi equal to 2 pi. Okay. So, whenever this restriction put and this natural way, this parameter comes which quantized form. Okay. So, similarly here, so to adopt this equation towards the associated Legendre equation, differential form of this associated Legendre polynomial. So, for that few steps one has to introduce. So, first we have to introduce this a dimensional independent variable. Here R have dimension. Okay. So, this rho is basically here this dimension independent variable rho. So, here this equation we will try to make it dimension independent in terms of dimension independent variable. Okay. For that, so let us here just we consider that rho equal to beta, beta is some constant, we do not know what it is, and also we consider here E are here in this equation, we consider here that E is less than 0. So, E can be less than 0, it can be greater than 0. So, when E is less than the 0, then we tell it is bound state, okay, bound state. When E is greater than 0, so it is not bound state, unbound state, okay, continuous state, okay. So, we are interested for bound state for this for our system, okay. So, that is why here we will consider that E is less than 0. That means, E I can write minus mod of E, okay. So, considering this one, if you just put this rho equal to beta r in this equation, okay, and E equal to minus mod E, okay. So, immediately from there it's one can write this one, okay. Just introduce this one, divide, multiply with some parameter, adjust them, and you will get this is straightforward, okay. Now, from here basically in this form you see, again as I told, our aim is to go towards this equation similar to this form, okay. So, in this form, so here this is constant basically, right. Beta is involved, nature of beta we do not know, okay. But aim, as I told, this rho is independent dimension. So, I expect that beta should be, this dimension of beta should be inverse of length, okay. So, later on we will see it is correct. So, this and then so this we are taking this equal to 1 by 4, again this for convenient. So, I can take these terms, beta will be such that, so this value will be 1 by 4, and here this term we have taken another constant lambda, okay. So, then if you take this one, so we can write this, okay, we can write this equation like, and so this from here, so this equal to 1 by 4. So, beta square will be this 8 mu E, 8 mu E, 8 mu E by h cross square, and lambda equal to this. So, this I can write beta value here I got, I will put beta value, okay. So, z square by h cross, z is square by h cross, because yes. So, beta value square root of this one, square root of this one. So, here mu yeah, I think 2 e. So, beta, this 1 by beta basically, no, 1 by beta. So, h cross will go up. So, square root of this h cross. So, here h cross square was there. So, 1 h cross will go. So, this yeah. So, here basically anyway. So, it is not difficult one, lambda equal to z square by h cross mu by 2 e to the power half, okay. Interestingly, you can see that if I take lambda equal to n, then immediately from here you can see that this E. So, I have written E n, lambda equal to n. So, lambda I have written E n equal to basically minus E mod E equal to minus this sign, and here you can see this mu here square of this one n lambda, then I will make it square n square, okay. So, this n square lambda square n square equal to this z square e to the power 4 by h cross square, and this mu by 2 mod E. So, now E will be equal to just this minus mu z square e to the power 4 by 2 n square h cross square, okay. So, here lambda is whatever you consider is nothing but n. This is after further long calculation one can show that lambda is n, and it can have only positive and positive integer, and it is the principal quantum number, okay. And it has relation with the L, it has relation with the L, because this I have taken lambda, this nothing but L n, and that the L is here. So, from this equation, this quantization of L and quantization of n we will get, in natural way we will get, and already we got the energy value, okay. So, whatever energy we got from Bohr theory, exactly this energy we got, okay. And that is why from Schrodinger equation, that energy of the system, okay, it is the quantized, and it depends on only principal quantum number, it does not depend on L and ML, although in this Schrodinger equation, when you are solving this, ML, L, N all has come, but energy depends only on. So, the same result as from Bohr theory. So, on Bohr theory, on ad hoc basis we got the result, but here we are getting in natural way, here we are getting in natural way, okay. And but there are some long calculation. If you do the calculation in details, you can find out, but here briefly I have calculated, and I tried to show you that that how, from where this in natural way, how this ML is coming out, N is coming out, L is coming out, okay. So, here we really need to do further calculation, but I will avoid it, and finally if you calculate proceed, so you will get this form of this function R. So, R is equal to some constant C, right, e to the power minus rho by 2, rho to the power L, and then this associated Legendre polynomial, okay. So, this the form, this will be the form of psi n L. So, let us accept this one without further long calculation. So, this my solution, and I got the energy level, and I got also this principal quantum number, and from when we will do this long calculation, then one can see this L is the magnetic quantum number, orbital quantum number, okay, and it can take value 0, 1, 2 up to n minus 1. So, that part I could not show you, for that one has to do more calculation, but let us accept it, and it will come in natural way, but we are more interested to discuss physics considering this wave function, okay. Energy already from Bohr theory whatever we got, so that same energy we got, but additional things from this quantum mechanics solving the Schrodinger equation, what we are getting, that is basically we are getting wave function, form of wave function for our system. And if you know the form of wave function of a system, you can know many things, okay. You can know many things about the system. So, next we will see this, what is the importance of the wave function and how it helps to describe the system, okay. So, I will stop here. In next class we will discuss physics considering these wave functions. Thank you.